Imagine watching a 30-ton war machine roll off a factory floor every single hour, 24 hours a day, 7 days a week. Now imagine that same factory just 18 months earlier took 19 full days to build one tank. This isn't science fiction. This is the story of how one stubborn genius named Charles Sorenson defied the entire United States military establishment, broke every rule in the manufacturing handbook, and created an unstoppable avalanche of American steel that buried Hitler's army beneath sheer numbers. What he did seemed impossible. Army generals said it couldn't be done. Engineers called him insane. But Sorenson had a secret weapon that the Axis powers never saw coming, and it wasn't better armor, bigger guns, or tactical brilliance. It was something far more devastating. The crisis that nobody saw coming. August 14th, 1942. The massive Detroit tank arsenal in Warren, Michigan, stretched across the horizon like an industrial cathedral. Inside this cavernous space, plant manager John Carswell Caden stood with a stopwatch clutched in his hand, his eyes fixed on hull number 217. Around this stationary steel beast, workers moved with the precision of master craftsmen. They had been trained by Army ordnance specialists, and their training showed. Every single weld met rigid inspection standards. Every bolt received precisely calibrated torque. Every movement followed the official technical manual to the letter, but something was deeply, terrifyingly wrong. Hull 217 had been sitting on that factory floor for 11 days. According to the current production schedule, it would need another 8 days before completion. 19 days total. 19 agonizing days to produce a single M4 Sherman medium tank. Caden did the mathematics, and the numbers told a story of impending disaster. At this rate, the Detroit tank arsenal, proudly proclaimed as the largest tank factory in the entire world, would produce approximately 420 tanks annually. The United States Army had requisitioned 10,000 tanks for 1943 alone. At current production rates, Detroit tank arsenal would need 24 years to fulfill a single year's order. 24 years. The mathematics of defeat were being written in man-hours and assembly time across that factory floor, and almost nobody in management noticed. Almost nobody. A 47-year-old civilian production consultant named Charles Sorenson was hunched over a requisition form, scribbling calculations on its back. This wasn't just any consultant. Sorenson had spent 36 years at Ford Motor Company, where he had revolutionized automobile assembly alongside Henry Ford himself. Now conducting an unauthorized time-motion study of tank construction, what he witnessed violated every single principle of efficient manufacturing that he had spent his entire career developing and perfecting. Tanks were being built like custom machinery. Crews worked on stationary vehicles, walking around massive hulls to install components piece by piece. It was craftsman production, the kind of approach you'd use to build a luxury yacht or a custom locomotive, being applied to industrial warfare. It was methodical. It was precise. It was impossibly catastrophically slow. Sorenson's calculations indicated something that seemed insane. With proper flow manufacturing principles, tank production time could be reduced from 19 days to 48 hours. 48 hours. The skeptics and the madman. When Sorenson first shared his calculations, his colleagues thought he had lost his mind. Army ordnance officials didn't just disagree with him, they were offended by the very suggestion. Tank construction, they insisted with absolute certainty, wasn't automobile assembly. The complexity involved, the precision requirements, the specialized components, all of these factors demanded the methodical, time-consuming approach currently being employed. Brigadier General James Wesson, Chief of Army Ordnance, stated flatly that what Sorenson proposed was technically impossible. Period. End of discussion. Tanks were not automobiles. They couldn't be built like automobiles. Anyone who suggested otherwise simply didn't understand tank manufacturing. But here's what they didn't know about Charles Sorenson. This was a man who had taken Henry Ford's revolutionary vision and turned it into reality. In 1913, Sorenson had helped create the moving assembly line that reduced Model T production time from 12 hours to 93 minutes. He had transformed Ford Motor Company into the largest automobile manufacturer on the planet, and he had done it by questioning assumptions that everyone else accepted as unchangeable truth. Charles Sorenson was about to do it again. His impossible trick, applying continuous flow assembly to tank production, would transform American armored vehicle manufacturing from artisanal craft to industrial mass production on a scale the world had never witnessed. Within 18 months, the Detroit tank arsenal would be producing one complete Sherman tank every 60 minutes, one tank per hour, 24 tanks per day, 168 tanks per week. This production rate would create an armored avalanche that would bury the Wehrmacht under American steel so deep that German industry could never dig itself out. But getting there would require Sorenson to battle not just technical obstacles, but the entire institutional weight of military tradition and engineering orthodoxy. The roots of catastrophe. To understand why American tank production was failing so spectacularly, we need to rewind to June 1941, 6 months before Pearl Harbor dragged America into the war. The United States Army was watching with growing horror as German panzer divisions swept across Europe like a mechanized tsunami. French armies crumbled. British forces evacuated from Dunkirk. The Soviet Union reeled under Operation Barbarossa. The age of armored warfare had arrived, and America was unprepared. The M3 Lee medium tank, America's frontline armored vehicle, was already obsolete. It was inferior to German designs in almost every meaningful category: armor protection, firepower, mechanical reliability, and tactical flexibility. The Army didn't just need a new tank, they needed a new tank immediately, and they needed it in quantities that seemed mathematically impossible. American engineers rose to this challenge with remarkable speed. The M4 Sherman medium tank was designed in just 78 days, between April and June 1941. This breakneck design pace required compromising on technical sophistication in favor of production efficiency. The Wright R975 radial engine was already in mass production for aircraft, so they used that. The 75mm main gun used existing ammunition stockpiles, eliminating development time. The suspension system adapted proven components from earlier designs. The hull was engineered for welded construction to minimize complex casting requirements that might slow production. On paper, the Sherman was designed to be easily manufactured. In practice, initial manufacturing proved agonizingly slow. The Lima Locomotive Works in Lima, Ohio, received the first production contract in August 1941. 6 months later, in February 1942, they finally delivered their first completed tank. 6 months for one tank. By April, production had gradually accelerated to one tank per week. One tank per week. This was utterly, hopelessly inadequate. The arsenal of democracy opens its doors. The Detroit tank arsenal represented America's all-in commitment to mass tank production. Construction began in September 1941 on farmland in Warren, Michigan, and the scale of the facility reflected America's industrial ambitions. The main building covered 1,600,000 square feet under a single roof. Let that sink in for a moment. That's nearly 37 acres under one roof. The assembly hall alone measured 1,200 feet long by 600 feet wide, large enough to fit multiple city blocks inside. Chrysler Corporation, which had never built a military tank in its entire corporate existence, received the contract to operate this mammoth facility. They brought extensive automotive manufacturing expertise, but immediately faced resistance from Army Ordnance Corps technical advisors who enter the revolutionary. Sorenson had been Henry Ford's right-hand man since 1906, transforming Ford Motor Company into the largest automobile manufacturer on Earth. He had pioneered the moving assembly line techniques that reduced Model T production time from 12 hours and 30 minutes to an astounding 93 minutes. He had essentially invented modern mass production as we know it. Sorenson had retired from Ford in 1941 after disagreements with Henry Ford's son, Edsel, but retirement during wartime felt like desertion to this man who had immigrated from Denmark as a boy and considered American success his personal sacred mission. When the War Production Board asked him to consult on tank manufacturing, Sorenson didn't hesitate. He accepted immediately. His first week at Detroit Tank Arsenal confirmed his worst fears. Tanks were being assembled using methods that predated Ford's 1913 assembly line revolution by decades. Workers moved around stationary products instead of products moving past stationary workers. This difference seemed subtle, almost trivial to casual observers. But to Sorenson's expert eye, this difference had profound implications for efficiency. It was the difference between 19th century craftsmanship and 20th century industrial production. The unauthorized study. Sorenson spent the next 2 weeks conducting exhaustive, detailed time-motion studies. He photographed operations from every angle. He interviewed workers about their techniques and challenges. He calculated theoretical production rates based on different organizational approaches. His analysis identified 173 discrete operations required to assemble a complete M4 Sherman tank. Under current methods, these operations required an average of 9.7 hours each. Total assembly time reached 456 hours, spread agonizingly over 19 days. But here was Sorenson's revolutionary insight. Most of these operations didn't actually require 19 days to complete. They required 19 days because of waiting time. Time waiting for the previous operation to complete. Time waiting for tools and components to be delivered to the work site. Time waiting for inspection approval from Army ordnance representatives. Time waiting for specialized crews to become available. Time waiting for equipment. Time waiting for materials handling. The actual productive work time was maybe 30% of total elapsed time. 70% was pure waste. Sorenson's solution was elegant in its simplicity. Eliminate waiting by implementing continuous flow manufacturing. Instead of workers moving to stationary tanks, tanks would move past specialized workstations on a continuously flowing assembly line. Each workstation would have all necessary tools, equipment, and components immediately available. Workers would perform the same operation repeatedly, developing extraordinary speed and efficiency through repetition. Inspection would be continuous rather than batch-oriented, eliminating approval delays. Materials would flow to workstations automatically, eliminating delivery delays. The numbers were staggering. Sorenson calculated that continuous flow assembly could reduce tank production time from 456 hours to 48 hours, from 19 days to 2 days, a 96% reduction in assembly time. The battle of bureaucracy. When Sorenson presented his proposal to Chrysler management and Army ordnance representatives in August 1942, the reaction was immediate and hostile. This wasn't polite skepticism. This was institutional resistance bordering on fury. Brigadier General James Wesson, Chief of Army Ordnance, stated categorically that tanks were not automobiles and couldn't be built like automobiles. The precision requirements alone made continuous flow assembly impossible. Tank hulls had welding tolerances measured in thousandths of an inch. Turret mounting required precision alignment that couldn't be achieved on moving assembly lines. The weight of components made continuous motion impractical. The complexity of weapon systems required specialized technicians who couldn't work on moving platforms. Chrysler's engineering staff enthusiastically agreed with General Wesson. They documented multiple technical obstacles that supposedly made Sorenson's proposal impossible to implement. Tank hulls weighed 15 tons, far too heavy for standard industrial conveyors. Turret installation required massive overhead cranes that couldn't operate over moving assembly lines. Final drivetrain assembly involved components weighing over 1 ton each. Welded hull construction required stationary positioning for proper penetration and cooling of welds. Every single objection was presented as an insurmountable physical limitation, a law of engineering that couldn't be violated. But Sorenson hadn't survived 36 years working with Henry Ford by accepting impossible as an answer. He countered every objection with specific, detailed solutions. Heavy-duty conveyors designed for locomotive shops could easily handle 15-ton loads. He had seen such conveyors in operation. Turret installation could use mobile gantry cranes that moved with the assembly line, not stationary overhead cranes. Heavy components could be pre-positioned at specific stations using dedicated lifting equipment built into each workstation. Hull welding could be completed in dedicated stations where hulls paused briefly before continuing down the line. The welding didn't have to happen while the tank was moving, just during controlled pauses in continuous flow. The ultimatum. The debate continued through the first disaster. The first trial run began October 23rd. Results were absolutely catastrophic. Conveyors jammed almost immediately under the hull weight. The load distribution calculations had been wrong. Welding fixtures failed to properly position components. The tolerances were too loose. Workers trained in traditional methods couldn't adapt to station-specific tasks. They were accustomed to seeing an entire tank through completion, not performing one repetitive operation. Timing synchronization was impossible, with some stations completing work in 8 minutes while others required 20 minutes. Bottlenecks formed immediately. Army Ordnance observers watched the chaos with barely concealed satisfaction. They had been right all along. General Wesson declared the experiment a complete failure and demanded Sorenson abandon the project immediately and return to proven traditional methods. Chrysler management agreed enthusiastically, concerned about wasted resources and continued production delays, while resources were diverted to Sorenson's failed experiment. But Charles Sorenson refused to quit. He had seen identical problems during the Model T assembly line's initial implementation back in 1913. Early failures didn't prove impossibility. They simply revealed specific problems requiring specific solutions. Every failure was a data point, a lesson, a step toward success. Sorenson requested 2 more weeks to refine the system. Reluctantly, skeptically, they agreed. The refinement. Engineers worked 18-hour shifts, redesigning conveyor support structures with reinforced load distribution systems. Welding fixtures were completely modified based on actual hull geometry measurements rather than blueprint specifications. Real-world tanks didn't exactly match drawings. Workers received intensive retraining focused exclusively on specific station operations rather than general tank assembly. Sorenson literally redesigned training from scratch. Station cycle times were rebalanced by splitting operations that took too long or combining operations that finished too quickly. The second trial run began November 9th. Results improved dramatically, but remained far from perfect. Tanks did move through the line, but with frequent stops for problem solving. Production time for 3 tanks totaled 8 days, better than traditional methods certainly, but nowhere near Sorenson's promised 2-day construction. It was progress, but insufficient progress. The breakthrough. Instead of workers remaining at fixed stations while tanks moved past them, Sorenson created small specialized crews that moved with hulls down the line, performing their operations while tanks continued moving slowly. This seemingly minor modification eliminated station-to-station transfer delays while maintaining continuous motion. Workers weren't waiting for tanks to arrive. They weren't waiting for tanks to stop. They simply moved with the tank, working continuously. It was brilliant. The final test. If it failed, Army Ordnance would not just shut down the experiment, they would probably ban him from any further involvement in tank production and use his failure as proof that civilians should never interfere with military manufacturing. The pressure was crushing. Sorenson barely slept during the 48-hour test run. He watched every station, monitored every operation, adjusted procedures in real time as problems emerged. The results exceeded even Sorenson's wildest projections. 3 complete Sherman tanks, fully assembled, thoroughly tested, and ready for immediate combat deployment, emerged from the prototype assembly line in 41 hours total. 41 hours for 3 tanks. Approximately 17 hours per tank compared to 456 hours using traditional methods. A 96.3% reduction in assembly time. But the most important validation wasn't speed. It was quality. Army Ordnance inspectors crawled over those 3 tanks with microscopes and measuring instruments, desperate to find defects that would invalidate the results. Inspection revealed no significant defects whatsoever. Test drives showed all systems functioning properly. Guns, engines, transmission, suspension, electrical systems. Armor welds passed ultrasonic inspection with flying colors. The tanks were genuinely combat-ready, indistinguishable from traditionally assembled tanks, except for one crucial fact. They had been built in 1/20th the time. Brigadier General Wesson, The man who had declared continuous flow assembly categorically impossible just 2 months earlier, personally inspected all 3 tanks. He crawled underneath them. He test-fired the weapons. He examined welds with magnifying instruments. He found absolutely no evidence of rushed construction or compromised quality. On November 25, 1942, General Wesson authorized immediate expansion of Sorenson's system to the entire Detroit tank arsenal. The revolution had begun. The transformation. The entire factory floor, covering 1,600,000 square feet, needed complete reorganization. Thousands of traditional workstations had to be dismantled. New assembly lines had to be installed across that massive space. 40,000 workers needed retraining in fundamentally different techniques. Supply systems feeding the factory had to be completely redesigned. All of this had to happen while maintaining minimum production to meet urgent military requirements. The war wasn't waiting for American industry to get organized. Sorenson divided the factory into 4 parallel assembly lines, each capable of independent operation. This redundancy meant mechanical problems on one line wouldn't stop entire production. It also allowed continued traditional assembly on some lines, while others transitioned to new methods, maintaining production during the transformation. Line A began continuous flow operation January 7, 1943. Initial production was cautious, 1 tank every 8 hours. But as workers gained experience and engineers optimized procedures based on real-world results, cycle time decreased rapidly and consistently. By January 31st, Line A was producing 1 tank every 4 hours, 6 tanks daily. Line B converted February 15th. Workers who had been skeptical of the new methods were now seeing the results and wanted their lines converted. Line C followed March 1st. Line D, the final traditional assembly line in the facility, began continuous flow operation March 22nd. By April 1st, 1943, all 4 lines were operating simultaneously, producing 24 tanks daily, compared to 3 tanks daily just 4 months earlier. But Charles Sorenson wasn't satisfied. His original calculations indicated that 1-hour cycle time was theoretically achievable. The current 4-hour cycle represented only partial implementation of true continuous flow principles. Additional refinements were required, and Sorenson was obsessed with achieving the theoretical maximum efficiency. Perfecting the impossible. Sorenson's team designed a specialized turret mating station where hulls paused briefly while mechanically assisted arms, robotic in their precision but manually operated, lowered turrets with extraordinary accuracy. The pause lasted just 6 minutes, but this innovation eliminated a 30-minute bottleneck. Small improvement, massive impact. Engine installation presented similar challenges. The Wright R975 radial engine weighed 1,150 pounds and required precise alignment with transmission and cooling systems. Sorenson developed an automated engine dolly that carried engines alongside moving hulls, allowing installation crews to work while tanks continued moving. No pause, no delay, no bottleneck. Final drive installation, mounting the heavy transmission and differential units, required specialized lifting equipment. Traditional methods used overhead cranes, which couldn't operate effectively over moving assembly lines. Sorenson's solution was ingeniously simple. Mobile floor-mounted lifts that tracked with hulls down the line, moving synchronously with the tanks they were servicing. The lifts eliminated installation delays entirely. These refinements were implemented systematically through April and May 1943, with engineers documenting every improvement for potential application at other facilities. By June 1st, cycle time had decreased to 90 minutes per tank. June 30th saw 75-minute cycle time. July 31st achieved 63-minute cycle time, slightly faster than 1 tank per hour. The transformation was complete. Detroit Tank Arsenal, which had produced 12 tanks in April 1942 using traditional methods, produced 721 tanks in July 1943 using continuous flow assembly, a 60-fold increase in just 14 months. The statistical revolution. Traditional assembly methods required 456 man-hours per tank. Continuous flow assembly required just 48 man-hours. Labor efficiency increased by 950%. One worker in Sorenson's system produced as much as nearly 10 workers using traditional methods. Factory space utilization improved by 400%, as moving assembly lines allowed much denser arrangement of workstations. The same building could produce far more tanks simply through better organization. Material handling efficiency increased by 600% through automated delivery systems that eliminated time workers previously spent fetching tools and components. Quality defect rates decreased by 73% despite dramatically faster production, because specialized station workers developed extraordinary proficiency at their specific tasks. This wasn't just improvement, this was revolutionary transformation of industrial capability. The ripple effect. By year-end 1943, American factories were producing 2,100 Sherman tanks monthly. The enemy's nightmare. German military intelligence had estimated American tank production capacity at approximately 300 units monthly based on traditional manufacturing rates and their own production experiences. When actual American production exceeded 2,000 monthly, German planning assumptions completely collapsed. General Heinz Guderian, Inspector General of German armored troops and the architect of Blitzkrieg doctrine, wrote in his diary in November 1943, "Intelligence reports indicate American tank production has increased tenfold within 1 year. If accurate, this represents industrial capacity beyond our ability to counter. Germany was producing 540 tanks monthly at absolute peak capacity, pushing German industry to its breaking point. America was casually producing 2,100 monthly. The 4-to-1 American advantage made German victory mathematically impossible in any extended conflict. American armored divisions in Europe could sustain extended combat operations, knowing replacement tanks would arrive within weeks. Commanders could use tanks aggressively, accepting losses as acceptable operational costs because replacements flowed continuously from American factories." The Normandy demonstration. German forces destroyed approximately 800 through combat, a significant number representing fierce fighting. But replacement tanks arrived faster than losses accumulated. By September 1st, American armored strength in France actually exceeded D-Day levels despite 3 months of continuous combat. Meanwhile, German panzer divisions couldn't achieve similar replacement rates despite fighting desperately. The 2nd SS Panzer Division Das Reich, one of Germany's elite armored formations, landed in Normandy with 89 tanks. They received exactly 0 replacements during 3 months of brutal combat. By September, Das Reich operated with just 14 functioning tanks. The division was effectively destroyed as an effective armored formation, not through catastrophic battlefield defeat, but through simple attrition that German industry couldn't replace. The production cascade. The M7 Priest self-propelled artillery, mounting a 105mm howitzer on Sherman chassis. The M10 tank destroyer, optimized for anti-tank combat. The M32 tank recovery vehicle for battlefield salvage operations. All used Sherman chassis components, and this part's commonality, itself a direct result of Sorenson's mass production approach, simplified logistics enormously. A single supply chain could support multiple vehicle types. Mechanics trained on Shermans could service all these variants. Replacement parts fit multiple vehicles. The broader revolution, he demonstrated conclusively that military equipment production could achieve industrial efficiency previously reserved exclusively for consumer goods. The Army Ordnance Corps, initially hostile to civilian manufacturing expertise, eventually embraced continuous flow principles across nearly all weapons production. Artillery shell production implemented assembly line methods, increasing output from 2 million shells monthly in early 1942 to 18 million monthly by mid-1943. A 9-fold increase. Aircraft engine production adopted synchronized assembly, with Wright Aeronautical producing 1,500 R975 engines monthly compared to 150 monthly using traditional methods. Small arms ammunition production reached previously inconceivable levels, with Lake City Army Ammunition Plant producing 4 million rounds daily, using continuous flow loading lines. The transformation validated Sorenson's fundamental principle. Complexity doesn't preclude efficient production. It requires different organization. Breaking complex assemblies into simple, repeatable operations allows workers to achieve extraordinary proficiency. Continuous flow eliminates wasted time. Specialized tooling reduces skill requirements, allowing rapid training of inexperienced workers. Synchronized timing prevents bottlenecks. These principles, proven under intense wartime pressure in tank production, became foundational to all modern manufacturing. The human dimension. Under Sorenson's system, these exact same workers produced over 8,000 tanks annually, a tenfold increase in labor productivity. Workers on continuous flow assembly lines consistently reported less physical strain compared to traditional assembly. The key was eliminating wasted effort. Time previously spent searching for tools, carrying heavy components across the factory floor, waiting for previous operations to complete, constantly repositioning for different tasks. In Sorenson's system, specialized stations meant every single movement was the obvious contribution to the war effort. Watching completed tanks roll off assembly lines hourly rather than weekly provided profound psychological reward. Union representatives, initially deeply suspicious of manufacturing changes that might threaten jobs or safety, eventually became enthusiastic supporters when they saw the reality. The economic transformation. Warren, Michigan transformed from a sleepy rural township of 10,000 residents to a booming industrial city of 50,000 within just 2 years. Housing developments sprang up overnight. Schools expanded to accommodate workers' families. Hospitals were built to serve the growing population. Infrastructure, roads, water systems, electrical grids, all expanded dramatically to support tank production workers and their families. Similar explosive growth occurred around other tank production facilities implementing Sorenson's methods. Beyond tanks, the region produced aircraft engines, military trucks, artillery shells, and countless other war materials. But tank production remained the symbol of American industrial might, particularly those Sherman tanks, rolling off assembly lines at rates Germans considered physically impossible. The post-war recognition. The Rand Corporation's comprehensive 1948 study of industrial mobilization concluded that manufacturing efficiency improvements contributed more to Allied victory than any single weapons technology. The study specifically cited tank production as the exemplar of how civilian industrial expertise transformed military potential. Charles Sorenson received the Medal for Merit, the highest civilian decoration available, in November 1945. The citation read, "For exceptionally meritorious conduct in the performance of outstanding services to the United States in the field of industrial production. His revolutionary manufacturing techniques increased armored vehicle production tenfold, providing material superiority that proved decisive in achieving Allied victory." But Sorenson's impact extended well beyond wartime recognition. He became president of Willys Overland Motors in 1944. Applying continuous flow methods to civilian Jeep production. Later, as an independent manufacturing consultant, he helped establish production systems for companies worldwide, spreading American manufacturing expertise globally. His 1956 autobiography, My 40 Years with Ford, devoted 3 entire chapters to tank production, describing it as his most personally satisfying professional achievement despite decades of revolutionary automotive success.